Hi everyone, this is Sushravya from Sri Venkateshwara College of Engineering, currently pursuing my 8th semester in the Department of Computer Science. Today I'm here to present a technical seminar on design and research of music based on the Internet of Things. Coming to the contents of this presentation, we have abstract, introduction, concept and vision, technological components, design of IoMusT system, key implementation techniques, current challenges, related fields, and conclusion. When we come to the abstract, the Internet of Musical Things, abbreviated as IoMusT, is an emerging research field positioned at the intersection of the Internet of Things, new interfaces for musical expression, ubiquitous music, human-computer interaction, artificial intelligence, and participatory art. From a computer science perspective, IoMusT refers to the networks of computing devices embedded in physical objects dedicated to the production and or reception of musical content. Musical things such as smart musical instruments or wearables are connected by an infrastructure that enables multidirectional communication both locally and remotely. A vision for the IoMusT and its motivations is proposed, and then the 5 scenarios illustrating how the IoMusT could support augmented and immersive concert experiences, audience participation, remote rehearsals, music e-learning, and smart studio production. When we come to the introduction, the term Internet of Things broadly refers to the extension of the Internet into the physical realm by means of everyday physical objects that are spatially distributed and augmented using information and communication technologies. In the Internet of Things, the word things refers to the embedded systems that are connected to the Internet, which are able to interact with each other and cooperate to reach common goals. Things are characterized by embedded electronics, wireless communication, sensing, and or actuation capabilities. Turchet et al. Proposed extending the concept of IoT to the musical domain, considering IoMusT as a subfield of IoT, where the underlying technological infrastructure enables ecosystems of interoperable devices connecting musicians and audiences to support novel musician-musician, audience-musician, and audience-audience interactions. The main purpose of this paper is to provide a unified vision of the IoMusT paradigm. We will focus on technologies enabling the IoMusT as well as on current IoMusT research activities, drawing attention to the most significant contributions and solutions proposed over the recent years. The concept and vision describes that from a computer science perspective, we define a musical things as a computing device capable of sensing, acquiring, processing, or actuating and exchanging data serving a musical purpose, and the IoMusT as an ensemble of interfaces, protocols, and representations of music-related information that enable services and applications serving a musical purpose based on interactions between humans and musical things or between musical things themselves in physical and or digital realms. The music-related information refers to the data sensed and processed by a musical thing and or exchanged with a human or with another musical thing. Just like general IoT field, the IoMusT may encompass manifold ecosystems. An IoMusT ecosystem is composed of users involved in musical activities, for example, the performers and audiences, information and service providers, and forms around commonly used IoMusT hardware and software platforms, as well as standards. From the technological perspective, the core components of an IoMusT ecosystem are of 4 types: musical things, connectivity, applications, and services. When we come to the examples related to the components, musical things have smart instruments, musical haptic wearables, etc. Connectivity has wireless and wire network supporting in both local and remote communications, ultra low latency, high reliability, high throughput, high quality of audio and multimodal content, standards and protocols for the IoMusT, for example, supporting synchronization mechanisms. Services have like service for connecting smartphones to smart instruments, service for connecting smart instruments to social networks, service for creative content analysis, etc. Applications have examples like for audience members, enhanced concert experiences based on multisensory content provided by musical things. like remote audience participation in the music creation process during concerts. For musicians, it is remote rehearsals, interactions with the cloud directly from smart instruments. For audio engineers, we have intelligent live and studio production supported by smart instruments. For students, we have enhanced music e-learning with remote teachers or augmented experiences through mobile apps and mixed reality displays leveraging data from smart instruments. For music teachers, web-based apps for student assessment, progress monitoring, and individual or group feedback. When we come to the deep learning of musical things, we have the IoMusT vision that predicts that in future a new class of musical devices will be connected to the internet, which could have a transformative effect on how humans involved in musical activities, for example performers, audiences, conduct these activities and interact with musical objects, for example the musical instruments. We position musical things as a subclass of things, therefore they will be inheriting characteristics of things such as sensors, actuators, connectivity options, and software to collect, analyze, receive and transmit the data. The key factors of musical things are interoperability and synchronization. Secondly, we have connectivity. The IoMusT connectivity infrastructure supports multi-directional wireless communication between musical things both locally and remotely. The interconnection of musical things over local networks and or the internet is achieved by means of hardware and software technologies as well as standards and protocols governing the communication. The music performance puts particular constraints on communications. These requirements are similar to real-time telesurgery, virtual and augmented reality, and real-time automation, but are not required in the vast majority of IoT applications. When we come to the third component, that is applications, the various types of applications and services can be built on top of the connectivity, which targets users such as musicians, which can be composers, performers, conductors, the audio engineers, for example live or studio sound engineers, and audience members. Such applications and services may have an interactive or non-interactive nature. To establish interactive musical applications, real-time computations have particular importance. Analogously to the IoT field, the IoMusT can leverage web APIs and Web of Things architectures designed to serve musical purposes. When we come to the service component, the methods of communication between musical things could be defined in APIs based on a unified IoMusT API specification. The interactions mentioned above based on the exchange of multimodal creative content are made possible thanks to a set of services. For instance, these can be services for creative content analysis, for example, based on multi-sensor data fusion and musical information retrieval. Services for creative mapping between analysis and devices, or services for creative content synchronization, that is between the devices. When we come to the figure, we see that many arrows are connected, and here we have co-located performers, remote audiences, and co-located audience. When we come to figure 2, we have the block diagram of an IoMusT ecosystem involving performers and audience members. Here the contents are in the co-located field we have performers, musical things, and the service which is interconnected to each other with musical things and audience. And the performer 1 up till performer n is observed, then smart instrument 1 up till smart instrument n. And the below block diagram indicates which have in remote we have the contents performers and musical things, and vice versa in as same as above. Elaboration of the figures, we can see that in figure 1 the IoMusT infrastructure enables ecosystems of interoperable devices connecting musicians with each other as well as with audiences, which multiplies the interaction possibilities both in co-located and remote settings. Such ecosystems provide fertile grounds for the design of creative artifacts, providing novel types of affordances, including ways to monitor creative control or response to musical content associated to musicians and or audience members. Figure 2 shows that a conceptual diagram which has different components that are connected in our vision of an IoMusT ecosystem. As can be seen in the diagram, interactions between humans are mediated by musical things. The diagram shows interactions between performers and audience members, but it can be further extended to include other actors such as live sound engineers. live sound engineers, studio producers, composers, conductors, or educationalists. Coming to the design of IoMusT system, firstly we have system architecture. The whole system is mainly divided into a front-end data acquisition module, a central control system design module, and a wireless audio transmission module, and a user sharing exchange website module. The front-end data acquisition module uploads the information collected by infrared sensor, photosensitive sensor, and voice sensor to the central control system. The central control system design module is to identify the collected sensor information, including simple speech recognition. The wireless audio transmission module is equipped with Wi-Fi module on the audio to receive the song information transmitted by the central control system and play it out. At the same time, 5G communication mode can also be used. The user sharing communication network station is used to provide users with downloading their favorite songs, sharing with other users, and commenting messages. The system structure figure is shown below. Secondly, we have the design of data acquisition module. The data acquisition module is mainly divided into infrared acquisition, light intensity acquisition, and voice acquisition. The main function of the infrared sensor is to collect information on whether there is a person in the room and transmit the information to the central control system through Wi-Fi. Next, we have the design of central control system. The hardware of the system mainly includes an ARM9 processor, SDRAM memory, flash memory, GPRS module, etc. The software system mainly supports various network protocols, Linux as operating system, C language as the main development language, combined with the actual functional requirements of the control system through the gateway interface, CGI program, and controller needs multiple device drivers. Next, we have design of wireless audio transmission module. The main function of this is to realize the central control system to convert the digital signal into an analog signal through Wi-Fi transmission. At the same time, at the receiving end, a Wi-Fi module is installed on the wireless audio to receive the analog signal transmitted, which is converted into a digital signal through the AD converter embedded in the audio so as to play. 5G based on STM32 wireless speaker system provides a solution with low cost, high transmission rate, low transmission distance, and high reliability. When we come to the key implementation technologies, we have firstly music signal feature recognition. The voice frames of the music feature test template and reference template follow the search path of DTW, which is dynamic time warping algorithm, to carry out music feature matching. Suppose that the reference template and the test templates are expressed as follows: S is equal to S of 1, S of 2, S of m, S of small m, S of capital M, and P is equal to P of 1, P of 2, P of small n, and P of capital N. Here, S and P refers to the feature test template and reference templates, where M and N are the total number of voice frames contained in the reference template and test template respectively. Small m and small n are the frame features in S and P respectively. The Euclidean distance is calculated as follows: P of small n, P of S of m is equal to 1 into h dash minus h into 2 into kr is equal to 1. Next, we have the speech recognition simple speech recognition algorithm. The speech recognition technology is to convert the vocabulary content of human speech into computer readable input, and then the computer makes certain processing. Because the system only needs to recognize some basic words spoken by users, such as the previous song, the next song, changing the background music, etc. After decades of development and accumulation, speech recognition technology has relatively mature solutions for general problems. For example, the voice interaction technology provided by Alibaba Cloud includes audio signal processing, interrupt wake up, speech recognition, synthesis, and other full-length voice interaction capabilities. Next, we have the RFID technology, which is the abbreviation for radio frequency identification. It is a kind of non-contact automated identification technology which can automatically identify the target object by radio frequency signal to obtain relevant data. Compared with the traditional magnetic card and IC card technology, it has characteristics of non-contact, fast reading speed, and no wear and tear. A complete RFID system consists of a reader, electronic tag, and application software system. The reader sends a certain frequency of the radio frequency signal through the transmitting antenna. When the radio frequency card enters the working area of transmitting antenna, the induced current is generated and the energy of the radio frequency card is activated. Next, we have the current challenges faced. The IoMusT inherits all the challenges of the general field of IoT. In addition to these, the practical realization of the envisioned IoMusT poses specific technological, artistic, pedagogical, legal, personal data, and creative data challenges. Firstly, we have the technological challenges. The realization of IoMusT vision described comes through the evolution of the network and services infrastructure as well as of the capabilities of musical things connecting to them. The connectivity features of the envisioned musical things need to transcend beyond the state-of-the-art technologies available today for the musical domain, because between a sensor that acquires a measurement of a specific direct auditory, physiological or gestural phenomenon and the receiver that reacts to that reading over a network, there is a chain of networking and information processing components which must be appropriately addressed in order to enable acceptable music interactions over the network. Secondly, we have the artistic challenges. The IoMusT differentiates itself from standard questions of the IoT by its artistic and performative application. As previously unveiled by dubious research, the enhanced availability of resources and the lack of relevance of the individualistic views and creativity may pose several challenges to IoMusT scenarios. Next, we have the pedagogical challenges. The IoMusT promises to expand the landscape of music pedagogy technologies. At the core of learning is conveying relevant information and feedback to lead to the understanding and improvement. Next, we have privacy, security, and legal challenges. The advent of digitization and the internet had an enormous impact on the music industry, in particular on its law and economics. In the same way, IoMusT paradigm brings challenges related to personal data, since musical things have capability of musically collecting, analyzing, and exchanging data related to their users. New business modules can emerge leveraging IoMusT data, for example, to provide services related to musical activities such as intelligent music production, music recommendation, and analysis of audience behavior and engagement. Ethical and responsible innovation are crucial aspects to take into account in the design of such services to ensure they are socially desirable and undertaken in public interest. Below we have the elaboration of security, privacy, and legal issues. Lastly, we have the related fields. In this section, we review keywords related to the IoMusT vision. The review aims to describe the results of various application domains that led to the emergence of the IoMusT field. We have network music performance systems. That is, the notion of musical performances over networks is almost as old as the networks themselves. Connected music performances go back to at least 1978, where the League of Automatic Music Composers connected 3 computers to exchange performance-centric information. The emergence of the internet brought a drastic expansion of the potential for network music performances. Then we have the IoT technologies. The background communication technologies of the IoMusT are wireless sensor networks, that is WSNs, the Internet of Things, and tactile internet. WSN refers to a network of nodes that can communicate via wireless networks for purposes such as monitoring, communication, and automation. Next, we have the interactive performances, that is, which commonly refers to practices that offer sensor-equipped live performers, for example, dancers or musicians, real-time performers, real-time control over media elements and events using their physical movements and gestures. With the advent of digital musical instruments for which the mechanical gestural actions from performers are severed from natural acoustical effects, there is an infinite number of possibilities to map control attributes to perceptual ones. Next, we have the ubiquitous music. Ubiquitous music refers to music or musical activities that are supported by ubiquitous computing concepts and technology. It has been defined as ubiquitous system of human agents and material resources that afford musical activities through a creativity support tools. Coming to the last slide, that is a conclusion. we conclude that based on the Internet of Things, IoMusT takes music as a starting point of research. It is a comprehensive research topic involving many engineering fields such as computer, communication, and information processing, defining music events from perspective of engineering. In this research, music events are defined as corresponding engineering links. Each link is mapped to the internet and realized by internet technology. The success of the IOMU strongly depends on standardization activities which are currently unrealized. The definition of standards for formats, protocols, and interfaces will allow the achievement of interoperability between systems. Issues related to security and privacy of information, which is common to the more general field of the Internet of Things, should also be addressed, especially for IoMusT systems deployed for the masses. Moreover, the research will need to address the challenge of how to design systems capable of supporting rich interaction paradigms that enable users to fully exploit the potentialities and benefits of the IoMusT. Thank you.